Hi, welcome back to my channel. So in this episode I would like to talk a little bit about the Portapack extension of the HackRF. So let me for a second just remove the spectrum analyzer display here. So in all my previous episodes I only use the basic HackRF, okay? Instead in this episode I want to show one of the functionalities of this Portapack extension. So of course one of the main idea of the Portapack is to be able to use the HackRF without a computer. And so in this video, to show that this is indeed possible, we just power the HackRF with Portapack with this USB battery thing. So let me just connect it. Okay, so the Portapack turns up, turns on, and as you can see, I'm not sure if you can actually, but it has the Havok firmware, which is one of the firmwares available for the Portapack and is probably the most developed one with the most functionalities. So the utility that I want to discuss today, also in relation with one of my previous episodes, is an utility which you can find in the Havok firmware. It's going to utilities, and then signal generator, and it is indeed a signal generator. So since this webcam unfortunately cannot focus sufficiently well for you to follow what I'm doing here, I will just try to tell you what I'm doing and then discuss the results directly on the spectrum analyzers. So this signal generator is very limited, but it's quite interesting in its simplicity. It's a FM modulator. So it can modulate some waves from 0 hertz to 99.999 kilohertz using FM. And of course the carrier of this signal can be from 1 megahertz to 6 gigahertz. So that's the basic functionality of this tool here. So for example, if I modulate a 0 hertz signal, so no signal at all, I will just get a sine wave. So this is going to be my basic setup, just a sine wave at arbitrary frequencies. And essentially this this part of the video will be very similar to my previous video titled the HackRF as a signal generator, except that instead of using a very basic new radio companion sketch as I did last time, I have this interface, this manual interface, which is quite handy. So let me again set the modulated signal to be 0 hertz, so no signal at all. Okay, I'm setting up the carrier at 100 megahertz, and let's just click start and see what happens at the level of the spectrum analyzer. Before I click start, let me just tell you something very important. I've connected the HackRF to the spectrum analyzer through a minus 10 dB attenuator and most importantly a DC blocker. I discovered that the Portapack extension always pushes 1.5 DC, 1.5 volts DC in its output. So this spectrum analyzer can handle 25 DC, so 25 volts DC, so should not be a problem. But with other devices you might risk to fry the input of the front end of your spectrum analyzer or your device. So just be careful. It's always a good practice to put a DC blocker and some kind of attenuator. Okay, especially with this type of things that are prototypes from China. Really, it's not something you should trust too much with some expensive equipment like a spectrum analyzer. Anyway, enough about that. So we click start, and there we have our signal. So let's try to see here. Wait a second. So the markers. So let's lower the amplitude slightly. So the reference now is at 10 dBm. So I'm outputting at the maximum power possible, which here on the Portapack is named 47 dB. As you can see, if I do a peak search, I'm getting my signal at 100 megahertz at about 0 dBm. So in reality this is, since we are attenuated by 10 dBm, it's a 10 dBm signal. So let's just decrease it. So gain, okay. So I'm just decreasing it to 40 at the moment. So we are going down. And as you can see, the interface is very simple. I can play around with the amplitude from 0 to 47. So just something that perhaps later we will check out also on the oscilloscope where it's macroscopic. But if you go to up with the gain, as before, we start to have a very bad side harmonics. So it's basically not worth, at the moment we're at 40, it's probably not worth going above 26. At the moment we are at 26 and the signal is pretty clean. We do not have any harmonics. So let me try to go to, let's say, just to make an experiment, 500 megahertz. Right. So we get this signal at 500 megahertz, and frankly it looks much better than what we observed in my previous experiment. So perhaps my sketch in, I don't know if it was not good enough, but here we are getting, so again, peak search, next peak, the main signal at 500 megahertz at minus 22 dBm. So in reality this is a 12 dBm, the gain currently is 26. And the noise floor here is, so let me just take the marker and go down, is at minus 57. So it's a good 35 dB down. Okay, so the signal is pretty clean, and I think we should be happy about that. And let's see what happened at 1 gigahertz. So yeah, same thing. So it's pretty good. And let's try one last thing, 1 gigahertz 500. Right. So it's either, I mean, again, perhaps it was the crappy connector here that I have from China was introducing some noise in my previous experiments. I don't know, but it looks pretty clean this time, and I'm very happy to see this result for my HackRF as a signal generator. In a way, using this Portapack interface is very easy to use. Now let's go back to 100 megahertz, and I want to see the shape really of the FM signal with the spectrum analyzer. So let me just take the frequency indeed to 100 megahertz, and the span, let's put it to 10 kilohertz. Okay, so we have a big zoom on the signal, and there it is. So our let's pick search and center the frequency at where the peak is. So this is what I've just done, and let's regulate also the amplitude so we can see the noise floor compared to the signal. Okay. So now, as you can see, the signal is well, I'm not sure if you can actually see it, but yeah, you can see the center frequency at the moment is 99.99707 megahertz. This is because I observed that the clock of my unit is not precisely 10 megahertz. It's 300 hertz lower than that, so it's actually 9 megahertz. So it's basically one digit. So it's basically this center frequency that we see at the moment. So where is it? Here, divided by 10. So 9.999707. So of course, when we move to 100 megahertz, the error is multiplied by 10. But that's okay. It's expected. It's expected because this clock is not temperature. I mean, it's not. The oscillator is not an oven temperature compensated oscillator. So anyway, that's good enough, and there's not a problem. I mean, at least for me in this context. Now, instead of just producing a pure sinusoidal function, I'm going to produce an FM modulation 1 kilohertz. So let me do that. And there we see the typical response of an FM signal. So at the moment, the resolution bandwidth is set at 100 hertz, so you can see it here. I'm going to improve this to 30 hertz, so we get even more resolution. And so we can see the typical Now it's going to take 33 seconds to do a single sweep, but at least we can appreciate the typical shape of an FM signal with the basal, here the peaks that are exactly, well, let's see actually. So let me find the peak. The peak is there. This is the carrier at 10 megahertz. And if I take a delta marker, I can move away from exactly 1 kilohertz, because this is the frequency we are modulating. And here we have this first harmonic. And then there is another one, and there will be all the other ones, at least mathematically speaking, in theory. And their amplitude is determined by so-called basal functions that you can read it in Wikipedia. I also have to study way more this topic. Anyway, so this is just to show you the functionality, one of the many functionalities of the Portapack. We have a shield on top of the HackRF, and we can use it to have a very quick access to the functionality of the HackRF as a signal generator. You see how quick it was to change frequency, to change amplitude, and to change, what is being modulated and stuff like that. So let me stop the HackRF. By the way, before unplugging the HackRF, never do that while it's transmitting, because you risk frying. You really risk to fry it. It's a front end. So I'm going to now set 5 megahertz, and before clicking to start, I'm going to connect it to my oscilloscope here. I want to show just a couple of things at lower frequencies. My oscilloscope can handle only 20 megahertz, so that's why I just moved to 5 megahertz. So let's not do that. Okay. So I'm attaching to the BNC a BNC adapter to this SMA cable. Done. And connecting the cable to the oscilloscope. Done. So as you can see now, the oscilloscope is set to DC coupling, and we have half volt per division on the vertical dimension. So you see that, so this is the ground, and this is DC coupling. So the HackRF is, even when it's not outputting anything, it's having a DC component, as I mentioned before, 1.5 volts. Okay, so it was really important to have a DC blocker to block this component. I couldn't find a way to remove it, so I think that the firmware of the Portapack always does that, so just be careful. Anyway, let's move then to AC component, so we don't need to worry about anything. And so I'm just going to now modulate 5 megahertz at 1 hertz. So just 1 hertz modulation, so you will see what happens. So let's increase a little bit things here. So I don't know if this is doing what I was expecting. Ah, yes, I have to. So let me do this. I'm changing the bandwidth. Just 1 sec. Okay, stop, start. So now the signal is being modulated in FM. The carrier is 5 megahertz, and the signal being modulated is 1 hertz sinusoidal. So you see the frequency is changing in frequency every second. So this is the effect that is now displayed in the oscilloscope. If we change the position just to see where the signal begins, where it's being triggered. So let me see if I can do that. Here. So this is the beginning. And so you can see this spring effect, right? So let me see if perhaps is more visible like this. Okay. So you see every second the frequency is moving from 5 megahertz up and down a little bit. You can control this little bit. It's the maximum you can set is 150 kilohertz. So the moment it's the frequency is moving from 500 and then minus 150 kilohertz and then plus 150 kilohertz. Okay, so this is the effect you see. And if instead of modulating a 1 hertz signal, I modulate a 2 hertz signal, You see, the modulation is faster. If I go to 3 Hertz, it's even faster, and I can, of course, move on and get very, very fast. Okay, so let's go back to modulating a zero signal. So I just have a perfect sine wave at 5 megahertz. So at the moment the gain is 26. If you remember before on the spectrum analyzer, we saw that above 40, above 26, it was creating some harmonics, the signal. So let's see what happens now if I start increasing the amplitude from 26 gain up. So let me reduce the amplitude so we can follow. Now we are at 31. So the distortion are not yet visible on the scope so much. They were visible in the spectrum analyzer, but not on the scope. Now we are at 40, and I think still nothing is clear. Maybe a little bit you have the feeling that this is not anymore a sinusoidal wave, but anyway, if I move up to 47, which is the maximum, you see how much a distortion we get. So I would say that on the oscilloscope, you get a decent looking signal up to gain 40, which is what I've set now. But we know from actually the spectrum analyzer that things are pretty clean when you set 26. Yeah. So it's quite possible actually that in my experiment that I did with New Radio Companion, was setting the gain too high. So it was 40, or I mean in these terms, in the terms I've written here in the Havok interface, it was too high. So it was creating unnecessary distortions. But once the gain is properly set, the output, as we saw from the spectrum analyzer, is pretty clean. So I would say this is a complete success. The HackRF with Portapack can be used as a signal generator in a reasonable way. So thank you very much for following this video. If you have any comments, please leave them below, and if you like the video, just push the like button. Bye.